Good afternoon, everyone. Thank you for joining Dalhousie Renewable Energy Society's webinar series. My name is Gina. I am the president of Dalhousie Renewable Energy Society. This webinar will be an opportunity to learn about energy storage research and sustainability in engineering. We have two prominent researchers today, Dr. Lukas Swan and Dr. Dahn of Dalhousie University. Before we proceed with today's event, I would like to acknowledge that Dalhousie University sits on the land of Mi'kmaq, the ancestral and unceded territory of Mi'kmaq people. Dalhousie Renewable Energy Society is a student group who promotes sustainable engineering and alternative energy source usage in engineering application projects. And we also host sustainability-focused events just like this. Sign-up link is in the announcement section for those interested in joining DRES, and we are always open for new members. Now, I am very, very happy to introduce our presenters today. First speaker is Dr. Lukas Swan. Lukas is an associate professor of mechanical engineering and the principal investigator at the Dalhousie University Renewable Energy Storage Laboratory. He has 15 years of experience with energy storage and renewable energy, where he focuses his R&D on unique, elegant, and robust solutions to transition from fossil fuels to renewable energy. Lukas has a broad range of experience with major battery chemistries. He has developed, tested, and evaluated an enormous variety of battery packs ranging from hand tools, electric vehicles, to freight trains, to grid storage, to remote islands. He is also a member of CSA and UL committees that have created and published international standards for energy storage systems. Lukas received his PhD and master's from Dalhousie University and his bachelor's from California Polytechnic. He lives in Cole Harbor with his wife and 3 young children. Our next presenter is Dr. Dahn. Jeff is recognized as one of the pioneering developers of the lithium-ion battery that is now used worldwide in laptop computers and cell phones. His recent work is concentrated on increasing the energy density, improving the lifetime, and lowering the cost of lithium-ion batteries. Dahn was born in Bridgeport, Connecticut in 1957 and emigrated with his family to Nova Scotia in 1970. He obtained Bachelor of Science in Physics from Dalhousie University and his PhD from UBC in 1982. During his years at Simon Fraser University in 90-96, he collaborated with the R&D team at NEC Moly Energy Canada. Jeff took up the Natural Sciences and Engineering Research Council and 3M Canada Industrial Research Chair in Materials for Advanced Batteries at Dalhousie University in 96 and held the position until 2016. In June 2016, Jeff began a 5-year research partnership with Tesla Motors Energy as an NSERC Tesla Canada Industrial Research Chair. This session is being recorded, and the recording will be available to you followed by the event. You are automatically muted, but please feel free to type in your question at any time of the session for a chance to win a prize. There will be a Q&A session after both presentations. And now, without further ado, I would like to welcome Dr. Swan to speak. Dr. Swan, it is all yours.
Well, thank you, Gina, and it's certainly a pleasure to be here today. I run the Renewable Energy Storage Laboratory at Dalhousie, so as you might imagine, there's lots of synergies between DRES and myself, and I've had the opportunity to observe a couple of different DRES events over the last year and a half, and have been really pleased at the developments that you've made and the progress and the education that you provided for the students. I'm very pleased to talk to you today about batteries and electric cars, and the follow-up speaker to me, I'm sure we'll be speaking on tremendous advances that are going on right now. I'm hoping to give you a little bit of a view into the past and possibly into the future surrounding those technological developments that I hope Jeff's presenting on. So without further ado, if we would pull up my slide deck, please. So today I'll be starting off and speaking about batteries in electric vehicles. So batteries are energy storage, of course, and electric vehicles are any type of vehicle with an electric drivetrain that's supported by an energy storage technology such as batteries. I have a long history in this. It started in the 1990s, and we had really unique vehicles coming out right then. There was a big push in California. In the upper left-hand corner, you can see me as a teenager driving a GM EV1. That car was full of lead acid batteries and handled like a pig correspondingly because it was very heavy. In the lower left-hand corner, there was a transition that happened in the very late 90s and the early 2000s to the use of nickel metal hydride batteries, which were far more energy dense and very powerful as well. And we had lots of different vehicles running around, such as that Ford Ranger there, which we were immensely proud of because it was a work vehicle. It was a utility vehicle that we could do a lot with. There was a real dry period in electric vehicles because I think the lead acid and the nickel metal hydride vehicles just didn't meet the requisite needs of the general consumer as a vehicle. And we went nearly a decade before Nissan, in the upper right-hand corner, introduced the Nissan Leaf. And this was the first mass market electric vehicle composed of lithium-ion batteries. And this was a fundamental change in performance, charge capability, range, and general reliability as well. Overall, I had a couple different Nissan Leafs, and there you can see me very proudly showing off one of the early ones that I bought. And this worked well for my family, but as my family grew and we went further, we ended up needing a bigger vehicle that could go a lot further. And we went way out on a limb and bought a Tesla Model X in early stages, and that's in the lower right-hand corner there. And I show you that simply because we travel over 1,000 kilometers a day when we're traveling, with 3 children and usually 3 adults in it as well, skis tied to the back, and plug into a super fast charging network that's available. And this stuff really works for general consumers at this point, even in cold temperatures. And I'm really proud of that, and I'm proud of that company in developing those vehicles and the other companies that are coming out with vehicles that are equals to that right now. I had the opportunity in 2010 to join Dalhousie and start working with students, and this has been an unbelievable experience for me, something that has been tremendous and unique. And with them, I've taken my skills and experiences in electric vehicles and batteries and started building cars and bikes and motorcycles and electrifying them in all sorts of different ways. And you can see a variety of my students, and including a tour of Dres to a vehicle we did last year, which was a 1970s Triumph Spitfire full of lithium-ion batteries now, trials motorcycles, and then hybrid tricycles there in the lower right-hand corner, which won an NSERC award a few years ago. And so it's been a real pleasure with working with undergraduate and graduate students on different vehicles that have been electrified, and they learn all about the energy storage capacity, the power needs, how to physically mount things, how to thermally manage those batteries, electrically interconnect them, and observe them with a control and data acquisition system. So there's a lot of skills to be gained from this. Right now I operate a laboratory. I call it my little kingdom. I really like it. There's lots of us in there, plenty of us in there today too, working on advanced battery systems, and it's a unique and well-positioned laboratory because it's a separate space, and we have dedicated HVAC and fire suppression and all kinds of unique capabilities. And if you'd like a tour of this, or you're interested in energy storage, please reach out to me in the near future. We aren't supporting tours at this exact moment, but hopefully we'll be doing so soon again. And we usually do about a dozen a year. And I invite you to come see and experience batteries firsthand. We do all sorts of different projects in our laboratory, operating power cyclers on various batteries and collecting data and performance information that helps us develop and create new control strategies so that those batteries are implemented into applications to achieve best performance. Best performance could be longest life, it could be most cost effectiveness, it could be greatest reliability. There's a whole bunch of different metrics that we work by. So we have a variety of different projects right now. Speaking about grid storage projects, we have a student, Mark Elliott, who just finished examining degradation of batteries and is launching a company with that. We have a student who also just finished working on space batteries for a CubeSat application that's going to go into space from Dalhousie University next year. He's now working as a program director down at the NSCC on all sorts of interesting energy storage topics. We do battery controls, and we worked on high temperature batteries, and right now we've got people like David Thorkauf and Williams learning how to operate different batteries and work with them. And today I want to talk to you about EV battery repurposing, which has been a main thrust for us for 5 years, and I'm about to tell you why. So if you're unfamiliar, these are mainstream vehicles that anyone can virtually go buy right now from 3 different automotive manufacturers, very high performance, exquisite range capabilities, long-term warranties, operable in all sorts of different conditions. And there's a whole host of other vehicles that have even come out since this wonderful picture that appeared in Motor Trend a year and a half ago, such as the Model Y and the e-tron and a whole variety, the Kona and so on. And these cars are hitting the market right now, but they're each unique and distinguished, and especially when it comes to the battery systems. Cars are selling like hotcakes at this moment in time, and we've got over 2 million deployed in the world of pure EVs, and that number is rapidly increasing as we go through time. And so this means that this technology is becoming relevant to everyone, getting more widespread, and that brings about a battery issue. So speaking directly to that battery issue, here's 3 different battery packs. They come out of the Nissan Leaf, the Chevy Bolt, and the Tesla Model 3 that I just showed you. These are pictures inside my laboratory. And while they all look physically similar, they have significant differences between them. On the left, the Nissan Leaf is composed of a large pouch cell that uses a lithium manganese oxide chemistry inside it and a passive thermal management system. In contrast, the Chevrolet Bolt uses a medium-sized pouch cell, nickel manganese cobalt technology inside it, and a parallel liquid thermal plate conditioning system. And on the right, the very famous Tesla Model 3 uses a cylindrical type cell. It looks a lot like perhaps your thumb. You stare at your thumb, you'd say, geez, that's about the size of one of those cells. It uses a different chemistry inside, a nickel cobalt aluminum, and has a serpentine liquid thermal tube. And the reason I bring these things up to you is that these vehicles, they're great vehicles, but all vehicles experience end of life, and these will all experience end of life long before you or I experience end of life, hopefully, anyway. And in doing so, we have to take those batteries apart. We either need to recycle them or get rid of them in some way or repurpose them into something different. And I want you to recognize that each one's unique, and that might make that process very, very difficult. So when we get to the end of an EV's first life, and I've had lots of vehicles throughout my lifetime, and unfortunately some of them have ended via crash, and others have had early failure issues, and some have ended via old age. And here in Nova Scotia, where we dump lots of salt on the road, lots of them end because of corrosion. And I took this from the University of New Brunswick. They're trying to say, refuse to use extra stuff is the best at the top, and then reducing the amount of stuff comes second best, which is good. Manufacturing pushes really hard on that. And if you watched the Tesla Battery Day a few days ago, they were all about reducing not only cost, but manufacturing difficulties and so on. But third down is reuse, and that comes over recycle. And so a few years ago, seeing the market of EVs increasing substantially in number and count, I became focused on how do we reuse these batteries afterwards. And there's lots of ways to repurpose them. We can use them for stationary grid storage. You could build them into home energy storage units. We could put them into larger vehicles, such as a bus, perhaps. And there's probably countless other alternatives that hopefully some of you young innovators are examining right now. This isn't really easy, though, because of all of those different batteries that I mentioned just a few minutes ago. So along came some groups to develop a standard for repurposing of these EV batteries. And I was part of this group, and this standard was published jointly in Canada and the United States a year and a half ago. And frankly, I'm not particularly proud of this. There's aspects to it that I think make it rather unviable in some ways. And I'm looking forward to taking another stab at this as we've gained experience going forward. I think the real problems with this are that the amount of testing and handling of used battery packs before they could be repurposed into a secondary application is so much that it will render it economically infeasible. And to speak to that, what I really mean is that when you build something new, you have mass scale behind you, and you can really drive the costs down. But that doesn't mitigate the fact that you have to deal with these batteries at the end of life. And so even if those costs continue to go down, we have to do something with the batteries when they reach the end of life in an electric vehicle. And so I'm looking forward to this standard getting better in due course, and maybe some of you as engineers applying this standard for new product development or at different sites or developments that occur across the world in energy storage. And hopefully it'll get better and more useful, I think, in due course. So we have a real problem in our group with how do you deal with each unique individual battery that's coming off, and we think we've come up with a practical and a viable economic solution. It's something that we call the mixed battery array. And so contrary to what a lot of groups are doing right now, where they work with one battery type and they take it all apart and reconfigure it into different modules that get put back together into singular user devices, we want to use the whole pack when it comes out of the car. We want the ability to very quickly jump out any cells that might be bad, apply an independent battery management system to that, and then integrate a whole bunch of those different batteries onto a large scale energy storage system. And when I say large scale, I mean very large scale. I don't want to work with anything less than, say, 1,000 or 10,000 batteries at a time. But that scale is coming. There's hundreds of thousands of cars in Nova Scotia alone. So it tells you that, yep, that scale is really coming. And everybody, of course, wants a different model car. Some people like a truck, some people like a minivan, some people like a sedan. And technology progresses throughout time. And so we've created an adaptable methodology here in the mixed battery array to account for those different sizes and shapes and thermal formats of batteries that I just mentioned to you earlier. And we think we've created something that is economically viable in the sense that using the whole pack instead of breaking down that pack and rebuilding it into something different represents a significant time savings and utilizes the original components of the battery from the EV to a greater extent. So what does this all look like? Well, BMW's taken a stab at this. Large racks, big facilities, all interconnected batteries. Each one of those silver rectangle boxes is a unique battery pack, but you'll notice that they all look identical. So we don't want to do this. We want to do something different where non-homogeneous packs come in and all get interconnected. And so we're working right now on how do we physically lay that out? How do we electrically interconnect that? And how do we control that? And the controls are critically important. This is because different batteries have different performance characteristics. And when I started off this talk, I was mentioning that the Nissan Leaf has passive thermal cooling, and the Tesla and the Chevrolet have active thermal cooling. I'm not going to show you too many charts, but here's just one. So the passive cooling is on the right, and the active cooling are on the left. And we've run these batteries at different rates to determine how long they take to recover after a cycle, to thermally reacclimate to a temperature where we can begin the next cycle. And so 4 in this instance underneath any one of these batteries refers to a 4-hour cycle, and that would be for something like peak shaving on an electricity grid, where you all come home, turn the electricity on, the lights on, and the heat in your house, and that peak lasts on our Nova Scotia network about 4 hours. And you can see that the parallel active cooling and even the series active cooling, they spend about 4 hours in discharge and another 4 hours in charge, so they can really handle that. But as we move over to the air-cooled or passive air-cooled systems, they can do that too. But if we went at a 2-hour rate, a higher rate, to achieve additional benefits, they spend significant amounts of time waiting to cool down after that discharge before they're allowed to charge. And this means that they have limited applicability. So our research right now is focused on determining these differences. It doesn't mean the packs on the right are bad. It just means that they need to be used for a service, an electrical grid service, that is more appropriate for the way that they were designed. And there's lots and lots of electricity grid services out there. You'll probably hear the term stacked electricity grid services, which is doing 2 things at once to enhance your revenue, hopefully while avoiding penalties by not being able to provide for any one individual application. And so what we're working on is how do you apportion a call for a service across, say, 10,000 battery packs? How much do you send to the first pack, the second pack, the third pack, the 999th pack, and so on? And how do you operate those, because they're at different ages in life? And I think that's the real research frontier right now for what do we do with repurposing of EV batteries. To close up my presentation, I wanted to mention a couple of engineering opportunities for batteries and EVs. You're in Atlantic, Canada. We're not a vehicle manufacturing area, and we don't have large-scale battery manufacturing here at all either. But if you're in electrical engineering, there's all sorts of distribution circuit designs, end user circuits, and circuit sharing that might be needed, especially in multi-unit residential buildings, to integrate storage. So there's a lot of work that needs to go on there to approve different methods that we can integrate storage within homes and buildings. If you're a civil or a planning engineer, we need to look at new layouts of how do we get storage on the ground and get it there fast, making it long-term, and the ability to withstand frost and so on. And if you're a mechanical engineer, we'd be looking at orientations or layouts, thermals, and safety systems. Within the vehicle category for Nova Scotia, I'd say transit or municipal vehicles are something good you could get interested in and probably have a significant impact in. We'll certainly need a lot of engineering analysts to determine how energy storage systems can play roles in systems and meet generation and load and have coordinated control. So if you're interested in computer modeling or something like that, then this would be the way to go. And in end of life, where we're working in repurposing, it's just one little facet. And I want to, it's a little humbling sometimes to think about that, but we're affecting one area, but there's lots of areas to go on. So if you're interested in energy and batteries and want to do something, I would encourage you to go into these. And I want to close with a thought for those of you who are presently in a transition. So I know we're speaking here, we're at a university. A lot of you are either joining university out of high school or about to graduate university, and I'm thinking of you because it's a transition time right now. And transitions aren't easy, and particularly in this year, transitions are even more difficult. And a couple of words for you. I think you should love where you live and what you do, and if you don't, you should move on. I really think you're important. I think you should live it, buy into your passion, and gain experience by hands-on access to stuff. So I've always been buying cars and selling cars and buying batteries and selling batteries, and I've gained a lot of experience from that. And I'd encourage you to get your screwdrivers out, take things apart, look inside, and figure out how they work. Seek out others that are working on the same things that intrigue you, people that are enthusiastic and not cynical, people that really want to try and move things forward and technologically advance things going forward. And finally, to take leadership roles. It's the right time and the supports are there. I have students emailing me almost daily right now about different ways that they're going to commercialize their technologies, and they're finding those supports and guidance, especially from the province of Nova Scotia and the variety of governmental organizations and startups and sandboxes and things that are around. And it's that time to take that leap if you're interested in it and want to take a leadership role in there. And with that, I'm all done with my presentation, and thank you very much for the time to speak with you today. I hope I said something that caught your attention. I'd be very delighted to take questions after our next speaker has had a chance. Back to you, Gina.
Thank you very much, Dr. Swan. The presentation was very intriguing and about the exciting opportunities in engineering as well. A reminder for everyone to type in your question at any time of the session for Q&A later. We'll be welcoming Lukas back for that session. Our next guest, I'm very, very excited to host him as well, is known by many students as the Tesla Prof. As mentioned in his bio, his recent work is concentrated on increasing the energy density, improving the lifetime, and lowering the cost of lithium-ion batteries. Dr. Dahn, the mic is all yours.
Thank you very much, Gina. I'm very happy to be able to give a short presentation here at the DRES webinar. So if I could have the first slide projected. I really want to talk about how good a lithium-ion battery can be and what are the consequences of that. So this is work that's been done in the last few years in our Tesla partnership by the students and postdocs listed here on this first slide. So I want to start by just telling you a little story that's a little bit weird. So we published this paper in September 6, 2019, so about a year ago. It has a very strange title. It says, a wide range of testing results on an excellent lithium-ion cell chemistry to be used as benchmarks for new battery technologies. And the reason we publish this is because there's always people inventing or claiming to invent new wonderful battery technologies that are going to displace lithium-ion. And they generally compare their performance to crappy data from lithium-ion cells. So we wanted to put something out there that really showed where modern lithium-ion cells were. So in this paper, it just turns out I wrote a sentence in the abstract that said, we conclude that cells of this type should be able to power an electric vehicle for over 1.6 million kilometers, 1 million miles, and last at least 2 decades in grid energy storage. Well, that particular sentence caught the attention of Electrek, and the very next day on September 7, this thing came out. Tesla battery researcher unveils new cell that could last 1 million miles in robot taxis. And the whole internet went wild. This came out in Charged, I think. Tesla may soon have a battery that can last 1 million miles. Tesla's Jeff Dahn unveils million-mile battery cell. You know, so I wanted to just talk to you about how good lithium-ion cells are and what are the consequences of that. So the cells that were talked about in that particular paper, many of them are still testing today. And what we plot is the charge-discharge capacity of small lithium-ion pouch cells. They're probably about 1/5 or 1/10 the capacity of what's in your cell phone, but they are exact replicas of real lithium-ion cells. And we charge and discharge them, in this case, with a 1-hour discharge and a 1-hour charge. And every 100 cycles, we do a 20-minute discharge, and we do a half an hour discharge, and so on, and we call that a rate test. But really what I want you to look at is the cycle number axis here. It goes to 10,000 charge-discharge cycles. And these cells have been going for 3 years so far. These ones are being charged to 80% of their full capacity, 90%, 100%. And all of these show no evidence of failure at all after 3 years and 10,000 cycles. So, you know, it's pretty incredible. A well-designed lithium-ion cell can work like a charm for a very, very long time. And if you do the math and you say, look, let's just put these in a moderate range electric vehicle, 350 kilometers per cycle, 10,000 cycles, that's 3.5 million kilometers, you know. That's incredible. Like, no vehicle is ever going to go 3.5 million kilometers, at least not a passenger vehicle. So do we need batteries that are this good? I mean, is it really necessary? And it's actually even better than this. So here's some other data that just shows you that if you're doing this 100% depth of discharge, so this means charge all the way as much as you can and discharge all the way as much as you can, then you can see there's some small capacity loss that's taking place over these 20,000 hours of testing. 8,700 hours is a year. So this is about 2.5 years of testing. But look what happens when you just use the battery as most electric vehicle drivers would do. The majority of your trips are commuting to and from work, where you might go, you know, 50 kilometers, 80 kilometers, not the full 400. And if you're doing these short range trips, 25% depth of discharge, look at this, there's absolutely no loss. 2.5 years, 15,000 cycles. So when well-designed lithium batteries are used in vehicles, the lifetime is going to be incredibly long. And again, I come back to this and say, do we need batteries that are this good, right? And this is where you have to think about, what are we not doing that we should be doing? And one of them is what's called vehicle to grid. So when the vehicle is parked, it's plugged into the grid. With the modern internet and modern software, the vehicle is talking to the utility. You've told the vehicle to say, listen, Nova Scotia Power, you're allowed to charge me when I'm plugged in, and you're allowed to discharge me when I'm plugged in, but don't ever discharge me below 30% because I need to get home at night. And they should be paying you for this, for being able to store energy in your battery and recover it when they want. And this is where you need these very long lifetime lithium-ion cells, because your battery might do a couple of partial charge and discharges while it's just sitting there. You know, and with lithium-ion cells of the type that are used in some electric vehicles today, you do not want these extra charge-discharge cycles to be put on your battery pack while the vehicle is sitting still. But with a well-designed long lifetime lithium-ion battery, doing vehicle to grid is incredibly sensible. Then you have the ability to store electricity from wind and solar when you have lots of EVs plugged in, and you don't need to make as many large-scale grid storage facilities. So this is a really important thing to think about. That's why we need such awesome lithium-ion cells. And the first place where this should happen is in situations where you know exactly what the vehicle is doing every single day. A good example is a school bus. In the morning, the school bus is going to go gather up the kids, take them to school, and then it's parked. And it's parked when the sun is shining in the middle of the day. It should be charging at that point. And then when it's in the afternoon, the school bus takes the kids home. And then during the nighttime, it can be discharged into the grid, at the time of day that Lukas was talking about, when everybody's coming home, plugging in their, making dinner, turning on lights, running a TV. All these school buses can be discharging to just the level where they have enough electricity to make the first morning drive again. And all of this is coupled to the weather reporting, because if it's not going to be sunny the next day, you don't want to discharge all the way. So you think about the computer software that needs to be done to do this intelligently and smartly. It's a lot of work to do, but with an awesome lithium-ion cell, it makes enormous sense. Grid energy storage. If you're doing a situation where you have daily storage, 1 charge and discharge per day, that's 400 cycles per year. So 10,000 charge-discharge cycles is 25 years. And the data that I showed you earlier showed no sign of degradation over 10,000 cycles. So how long will those cells last? I don't know the answer. And if you're in the grid energy business, a lot of the models today are you sell an energy storage system to an energy provider. You make money one time when you sell this device. But if you take an alternative approach and say, listen, instead of selling this device, I'm going to lease it. I'm going to lease it at a fairly low cost. Well, once you get to the payback period, which might be 10 years or so, every other year, every additional year that the energy storage device lasts, you're making money in your pocket. So the longer it lasts, the better it is for you. And I think what will happen is a lot of energy storage providers are going to realize, hey, we don't want to sell these things. We want to be in the electrical storage business. We'll provide a service. We'll be paid by the utilities to store electricity, and we'll own that storage facility. And then the longer it lasts, the more money that you make. And Lukas talked about avoiding recycling and put EV batteries when the rest of the car rusts away and so on into a second use. And these very, very long lifetime batteries, they're definitely going to have a lot of lifetime left when the car rusts away. So what Lukas is doing is absolutely critical, totally important. And any students that get involved in repurposing, you can be sure that you're going to have a career that's meaningful for a long time. I was talking the other day to a CEO of a company that builds electric ferries, and he gave me an example of a ferry that they run between Sweden and Denmark. It's about a half-an-hour journey, a little bit less, across a body of water. It makes 46 trips per day. So that's 46 charge-discharge cycles per day, okay? So it turns out in 3 years, there's about 1,000 days. So that's 46,000 cycles in 3 years, okay? So some of these applications, you need incredibly long cycle life lithium-ion cells. I was talking to people at Pratt & Whitney the other day. They're talking about hybrid aircraft. You think, what the heck is a hybrid aircraft? Well, the idea is during takeoff, you need much more power than you do during cruise at high altitude. So the jet engines that are in an aircraft today have to be sized to deal with the very large power involved with takeoff. And if you could couple electric hybrid motor to an aircraft, you can downsize the jet engines and use electric boost, if you like, for takeoff and climb. And for a typical, short haul aircraft, they're doing 6 to 7 charge discharge cycles per day. So again, here's another example where you need a lot of cycle life. So these long lifetime lithium-ion cells are going to be incredibly important, in the future. So the future looks really good for lithium-ion cells. And if you were listening to Tesla's Battery Day presentation the other day, you just come away from there saying, this is amazing. Tesla's just moving forward at the speed of light. They're making upscaling their factories. They know they need terawatt hours of lithium-ion cells for both energy storage and for vehicles. And it's an incredibly exciting time, as Lukas mentioned. So I hope in the Q&A that Lukas and I can answer the questions that you have. And if people want to get involved, just like Lukas says, we give tours of our laboratory too. It's difficult during the time of COVID, but once COVID is gone, we're happy to have people come through on tour and take a look. So back to Gina.
Thank you, Dr. Dahn. We have a volume of questions for the speakers, so let us get right into it. The first question is for Dr. Swan. Recently, Tesla announced a new 4680 cell format. Tesla says they're reducing the structural elements within a pack and replacing them with batteries increases pack energy density. Do you think the cells are capable of being a structural member in a pack? And do you see any thermal issues with the larger format? Dr. Swan.
Well, thanks, Gina. This is a very interesting question. For everybody who's on the call, a 4680 cell means 46 millimeters in diameter, 80 millimeters tall. And Tesla presently uses 1865s and 2170s, so they're much smaller. So the cells they use today are the size of my thumb, but the cells they're going to use in the future are size of a very small Coke can, not the 12 or not the 355 milliliter ones, but smaller. And I think you might have projected that this was going to happen on the basis that they went from a smaller cell size to a bigger cell size already. But there are always limits to these things. The cells are placed in the floor pan of the car, and that means there's a certain height limitation to that you just can't get beyond. Otherwise, you need a lifted Tesla Cybertruck, I guess. So it wouldn't work for passenger cars. So we've got a length limitation. And then on the diameter, what happens is heat gets generated throughout the jelly roll in the cell, and it needs to be dissipated, especially under fast charging. And just as a quick aside, 15 years ago when I was working on EVs, everyone was concerned about the peak power draws under discharge. That's not the concern anymore. It's all about the continuous high rate charge powers. But that's what we want. We want fast charging cars. So you have to get that heat out in those situations. I've only seen one picture of their new cell design, but very conspicuously, there was a pretty large diameter hole in the middle of the cell where they start the wrap of the jelly roll. And it might be possible they'd run coolant through that. And if that was the case, it would cut down on the thermal path length substantially. I've also seen really interesting designs and been in an automotive manufacturer before that was immersing their cells in a dielectric oil to keep them cool, to fully surround them. So there's all kinds of solutions to the heat rejection problem that's out there. And I look forward to seeing the advantages of this. And I know Jeff and I have discussed on several occasions the different formats of cells, be it pouch cells or prismatic, which is rectangular cells, or cylindrical cells, and the advantages and disadvantages of each. And it seems that Tesla's really sticking with the advantages of the cylindricals while the rest of the industry is headed off principally for pouch. And they're really pushing the envelope on that. And so I look forward to someday having those batteries in my lab too and giving them a try and seeing the performance that comes out. But I think you can look forward to interesting thermal design solutions to accommodate the larger diameter cells. Back to you, Gina.
Thank you very much. Second question is for Dr. Dahn. Comparing hydrogen fuel cells and lithium-ion batteries, what are the advantages and disadvantages of the two?
Okay, thank you for the question. So I worked on hydrogen fuel cells from about 2001 to about 2013, as well as lithium-ion batteries. So I know something about both. And it's really very simple to think about what is the difficulty here. So if you have a hydrogen fuel cell, it needs hydrogen to be the fuel. And if you don't admit hydrogen produced by steam reforming of methane, because that creates CO2, you have to produce hydrogen by electrolyzing water, which is fine, but it's only about 70 to 80% efficient. And then the hydrogen has to be stored somehow, and on a vehicle that's stored in a compressed tank. And compressing the hydrogen is about 80 to 90% efficient. And then the fuel cell itself, when it's operating, is about 50 to 60% efficient. So when you multiply all these efficiencies together, you get about 35 to 40% efficient from the electricity that a solar panel or a windmill would generate going to the wheels on the car. Okay. Now a lithium-ion battery is about 95% efficient during charge and discharge, and there you go directly from the electricity from the windmill or the solar panel to charging the cell. So what it means is, if you want to use fuel cells in vehicles, you have to build 3 times as many windmills and solar panels to operate those fuel cells compared to lithium-ion powered cars. And for me, that's the big difficulty with hydrogen. Now, on the other hand, if you do have a situation where the sun is shining and the wind is blowing and you have nowhere to put that electricity, no one's using it, you got to put it somewhere, well then by all means make hydrogen and use it later. Back to you, Gina.
Thank you. Our next question is for Dr. Swan. What limits or barriers are there before energy storage as a technology can be made even more beneficial to power utilities?
Thank you, Gina. I'd like to expand that question just a little bit. There certainly are technical limits. Voltage is one of them. The cells go up to somewhere between 4 to 5 volts, and that was a drastic change from some of those electric vehicles I showed you from the late 90s and early 2000s, where cell voltages were 1 or 2 volts. It means you need much less number of connection counts and things like that, which is great. If we could get to higher voltages, that would be really good, but I think we're going to run out of the periodic table of elements, unfortunately. This second part would be energy densities. We'd really like to enhance that, or enhance power and so on. And I'm not so sure we'll get to too much higher energy densities. There's some really crafty techniques, but they often limit something elsewhere. And you might think of it as like a triangle with 3 points. And if you enhance energy density, you reduce life. And if you enhance life, you reduce power and things like that. Where I'd really like to see the technical evolution go is to incredibly high rate charging for batteries. I think that is absolutely opening for electric vehicles, because everyone compares fast charging to fueling up at a gas station, and that's about a 5-minute activity. So I'd like to see batteries that could charge in 5 minutes. There's a lot of technical hurdles to that, but I don't think it's impossible by any means. So that's the technical end of it. You specifically asked about the battery industry and deployment of energy storage, especially in utilities. And in that market today, what's really holding it back is red tape. The United States Federal Energy Regulatory Commission, FERC, has started to break down some of those barriers by mandating that utilities, which are often either vertically integrated or monopolistic, give consideration to the benefits of energy storage and price accordingly, that it can do multiple things simultaneously or brings advantages that might not be apparent with other technologies. And I think we're going to see some more of that going on. I would say it's holding the industry back strongly right now. That said, if you're looking for something that is on the horizon, that's invigorating to move forward, you see major countries and regions and communities and cities moving forward with bans on gasoline and diesel vehicles. California is the most recent, just in the last week, to say by 2035, passenger vehicle sales will be electric. And this is really good because the public has a propensity to be conservative with their technology, and they don't want to make a change. And sometimes these things need to be mandated when there's a widespread recognition that battery electric vehicles are in fact very efficient and can be used to charge with renewable energies directly or indirectly, and can provide some of the other benefits to the grid that Jeff was just mentioning about V2G and so on. And so I look forward to that. Unfortunately, as with all good political folks and regulators, they look 15 years out because they won't be in charge then. But I'm still enthused by this and think that you'll see way more change in the next 15 years than I've seen in the last 15 years. I think the technical people, the engineers and the scientists have done a remarkable job, and the technology is there and will continue to get better. And what's holding it back right now is some red tape. So I hope that those barriers are broken down, and if anyone listening to this is involved in that, business management or environmental science or anything, or environmental considerations, you should be working on those barriers to let the technology proliferate and progress us forward. Back to you, Gina.
Thank you. Next question is for Dr. Dahn. Over the last 4 years in partnership with Tesla Canada, how has the scenario in the battery industry changed since the start of your term?
Okay, thank you for the question, Gina. There's been a lot of changes in the last 4 years. I would say the most dramatic change is just the scale. You know, the amount of batteries that are being produced per unit time has been increasing probably 25–30% per year. And the scale of the factories that are being built these days, you know, they're measured in gigawatt hours of production. So a small lithium-ion battery of today would produce enough lithium-ion batteries that could store 1 gigawatt hour of energy. So that's a 1 gigawatt hour factory. All those cells would charge at the same time that would store a gigawatt hour. Larger factories are 50 gigawatt hours. Tesla is now talking about factories that are going to be a terawatt hour at a time. So it's incredible, the scale. And all of this means you need more lithium, you need more nickel, you need more manganese, and so on. So the resource suppliers have been ramping up to meet the need, and that will continue. At the same time, you know, people are getting ready for reuse, like Lukas, and recycling. Many companies have sprung up out of nowhere that are developing the needed recycling facilities to recover the lithium, nickel, cobalt, etc. From the spent and used cells. Now I notice there was a second question there that Gina didn't read, but it was what do I wish the average Canadian would know about energy storage? And my answer is I wish they all knew what a kilowatt hour was. Because many have no idea what a kilowatt hour is. They get their electricity bill, they say, oh, you know, it's $120, but they don't realize they're being billed by the amount of energy that they use. And they don't appreciate, you know, a kilowatt hour, a megawatt hour, a gigawatt hour, because these are the kind of things that you need to know when you're talking about energy storage for your home, your car, your town, your province, your country. And people just don't appreciate it. And to make the arguments needed to the politicians about energy storage, it would be nice if they knew what these things were. Back to you, Gina.
Thank you for identifying the second part of that question. Thank you, Dr. Dahn. The next question is for Dr. Swan, probably a little personal on a personal note. Please describe your average workday, Dr. Swan.
Well, thanks, Gina. I never have an average work day anymore. It's really strange. I jump around. Maybe I'd like to say something about the experience I have in a work day. Being a professor at the university means I get to engage with students, and they range enormously in capabilities and experiences. And so just to give you two examples of how much fun I have with that, a new student, Lauren Williams, joined my lab a month ago. She's an undergrad, second year, finished, and I'm teaching her how to crimp wires and operate a voltmeter. And that sounds rather simplistic, perhaps, but it keeps me sharp day in and day out, and I like that. And then at the other end of the spectrum, a student with a tremendous amount of experience, someone like Chris White, who's doing his PhD right now, walks in and says, I've got this new idea, and then proceeds to literally blow my mind with how in-depth he's thought things out and the solutions, the unique solutions that he's come up with to address a problem that 2 years ago I didn't even understand. And that continual development is really fun. And so I get to sit down with my group each day and say, hey, what did we achieve? And it's so fun to reflect on the fact that the things we're resolving today, we didn't even know were problems 3 years ago. And I've learned so much from them and from the classes they've taken from others. And that's been a real opportunity for me. And meanwhile, I contribute along with them. And so that's my work day.
Very interesting. Thank you. The last question. Unfortunately, we don't have time to answer all the great questions in the Q&A session. So this is our last question, and this is going to be open for both speakers. What advice do you have for students who want to start a career in the energy storage industry? What do you wish you had known in hindsight now that you are both seasoned engineers and scientists? What are you most excited about in your work? I will give that to Dr. Dahn first.
Okay, thank you, Gina. So actually, the very first question, Lukas had a slide that really showed nicely all the different opportunities in the energy storage space for engineering students. And if you listen to the Tesla Battery Day presentation and you saw you know, some of the things that they were showing, the advanced manufacturing, lithium-ion cells moving through conveying devices at incredible high speed, gigantic machines that cast entire body parts all at once. You just think materials engineering, mechanical engineering, electrical engineering, all these things. It's incredible. I'll let Lukas talk more about that, but I wanted to address the very bottom question, which is what makes me most excited about my work. And I got to tell you that as a researcher, sort of a materials developer working on battery chemistry, for us, when we have a real discovery, and maybe it's 5 times a year, where you have what I would call a eureka moment. It's incredible. It's you know, you're just getting chills running down your spine because you've figured something out. And generally that happens when a graduate student or an undergraduate student comes by and says, you know, Jeff, take a look at this data. And you take a look at this data and you connect the dots and you go, holy smokes, we've really figured something out here. And that is incredible. So that's what makes me most excited about my work. So I'll let Lukas have some minutes on this topic.
Well, thanks, Gina. I think the question, because I can't see it anymore, was how do students get more involved? And I'll just tell you how I got involved 10 years plus ago and re-engaged was networking. If you're interested in something, especially energy storage, obviously look around for information on the internet, but get out there and meet the people that are doing it. They're often interested in talking for a variety of reasons. They like to talk about what they do and tell you how great they are, but they're also looking for new people all the time that have strengths and experiences that they don't have, or that can be crafted into being tremendous engineers or scientists. We have a group of companies in Nova Scotia right now involved in the battery sector. Some have come out of Jeff's lab, and 1 or 2 have come out of my lab, and there's other ones popping up, and EV companies popping up right now, ripping apart EVs and building all new sorts of technologies from them. And I would strongly suggest those groups or any students interested in involving themselves in the sector, go to the local energy conferences we have here in Halifax. You can usually get in for a song, and shake hands with those people and ask if you can come visit their sites and facilities, where you will get more experience with your boots on the ground in 1 hour than you can in a week's worth of Googling, for sure. Experience is everything. Get your hands dirty, get in there and work with this stuff. That's a strength, I think. Back to you, Gina.
Thank you. I believe that's the strength as well. Now, that is all the time we have for questions. I would like to give a big virtual applause for both speakers. Thank you very, very much. Those people whose questions we asked from the Q&A session will be contacted soon for their prize. Now, thank you everyone on the other side of the screen for joining us today. The recording link will be available in our next newsletter. It was a pleasure having you on chat, and on that note, have a great weekend.